Hello, this is Zoe Turner, and this is my Lab 3 for macroscopic view of DC and RC circuits. In this lab, the purpose and principles are to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual conventional current and potential differences in a circuit, use voltmeters and ammeters to measure the potential difference in and current, to examine the behavior of ohmic resistors and capacitors, and the principles in this lab are the node rule, the loop rule, and the Ohm's law. And the main result of this lab is that voltmeters have a high resistance and capacitors are not charged instantaneously. So charge and energy conservation in series circuits. In this series, if an ammeter is connected backwards, the current is still reading the same. And when an ammeter is replaced with a voltmeter, it's considered as an open circuit, and the current is 0, and the volts is 3 volts. So before all of this, because of the loop rule, current 1 equals current 2, which is 0.2 amps. So continuing the charge in series, I put my little graph at every single node at what the volts were. And as you can see, between G and A, it was 0. This is because, well, I'll explain this later in the next slide, but the round trip of the entire loop is 0 volts. So why was that? Why, when we attached the voltmeter, when we altered the circuit, why doesn't the ammeter read change? It doesn't change because the voltmeter has really high resistance and essentially no current flows through it, making the ammeter's reading staying the same. You can see on the bottom right, it says R ammeter, and it's essentially 0. Same with wire. And now that we place the voltmeter with an ammeter in parallel with a 100 ohm resistor, what happens to the current through the other ammeter? Well, both ammeters change to 0.6 amps because the current is split at the node between the two paths. So for RC circuits, we have a different circuit on the right, and to observe the light produced at the 10 ohm bulb, what happens to the light? So at first the light is really bright, and then it slowly dims and goes out. You can see in my small graph or my small chart, I have it at the 10 ohm. And so now we disconnect the battery and connect the capacitor for the 10 ohm. What happens to the light? Well, same thing happens. Starts out really bright and slowly dims as the capacitor discharges. What happens to the current in both of the scenarios? Current slowly decreases until it hits 0. Why is that? Because time depends on voltage, or time-dependent voltage across a discharging capacitor. You can see in this little graph, starting at 0, it was really high, and as the time goes on, it just gets smaller, and smaller. It's a decreasing slope. And the RC is equal to 6 ohms farads. So here's some what if questions. First, what if we were doing this experiment in real life and we use an actual ammeter? What difference about the real ammeter? What's the difference about the real ammeter? And how would it affect the circuits hooked up to it? Well, the current would be really low because ammeters are not always top performing, and a real ammeter gives resistance, a simulated one does not. Number 2, what if we did this experiment in real life and used a real battery and a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In real life, it would take a lot longer for the capacitor to charge because the wires have some type of resistance. And because our ideal model has it at instantaneous full charge for the capacitor, in real life, it would just take, like I said before, a lot longer. In summary of this lab, we use Ohm's law, node rule, and loop rule to predict behavior of circuits with resistors in series and parallel, use voltmeters and ammeters to measure the potential difference in current, and multimeters to measure the actual difference in conventional current. An error in this entire lab may be because of a calculation. So that is a big warning sign for error. Thank you so much for watching my video. Goodbye.